and welcome back. We're in section 4.4. We're talking about compounded interest. Now, compounded interest is a lot like the question we did yesterday about the guy who got a raise, right? He got a raise of 6% every year, right? What was nice about that was the first year he has $40,000, the next year he has $42,400, but then he gets a raise on all of that. It's not $2,400 raise every year. The raise itself is getting bigger and bigger and bigger because it's like you're getting interest on interest on interest. That's what 4.4 is about, compounded interest. How does that relate? What is the difference? What does that mean? Well, take a look at this. Let's take a look at that salary problem. Let's think of it as a bank account. Your balance equals 40,000 times 1.06. That's a 0.06 to the t. Remember that? It was salary over time. Let's say it's your balance, your bank account, okay? So you start off with $40,000. You get 6% interest at the end of the year. You get $42,400 to start the next year, right? They get interest on interest on interest on interest. This is known as, it's compounded interest because you're getting interest on top of interest. But it's called simple interest because you're only getting interest once a year. But what if you got interest once a quarter? What's a quarter of a year? 3 months, right? Every 3 months? Or every 6 months. Say you got interest semi-annually, twice a year. Or quarterly, 4 times a year. 6 months, 3 months. How about if you got interest every month? Would that matter? Would that be better for you, your bank account balance? It would be, right? Let's see why. That's what this is about, okay? So what are we saying? That your bank account is your initial balance, say B sub 0, times 1 plus the interest rate to the t. That R is also known as APR. What? What's APR? You ever go to a bank and they say, oh yeah, this is a nice checking account. We got 2% APR. Ugh, whatever, yeah. Annual percentage rate, right? That's the APR, annual percentage rate. How much you get at the end of each year if you only had simple interest once a year compounded yearly, right? All right, let's change that up. What if I change it? What if I take the same exact problem, but now I get interest every 6 months, twice a year? How do you do that? You take 40,000 times 6%. I want to do this for half a year. Half as much. So instead of 2,400, I get, right, the 6% of 40,000 for the whole year was 2,400, right? But if I do it for half a year, I get 1,200, right? But what's good here is when you get interest at the end of the next 6 months, you're getting interest on the 1,200. So you're going to end up with more or less or the same as we did before, 42,400. You're going to get more. And if you compounded more times, say 4 times a year, 12 times a year, 365 times a year, 500 million times a year, you're going to get more and more interest. Can you get as much interest as you want? I'm going to go to bank B, not this bank sucks. I'm going to go to bank B that gives me so much interest I can say, give me $1 million at the end of the year. No matter what I put in as my initial balance. Does that work? No. There's a limit. There's a horizontal asymptote. We were talking about this in the homework, right? There's a limit to how much more money you're going to get, but you're going to get more money. The more compoundings, the more times per year that you get interest, the more money you're going to get. And eventually, if you take this to the limit, infinitely many compoundings in 1 year, what we call continuously compounded interest, you get the maximum interest. We're going to talk about what that is at section 4.5. That's Euler's number. Remember we talked about Euler yesterday? Euler's number E, that's where it comes from. It's going to come out of here, the limit of this process. All right, so let's do this. Let's take a look at, now, all right, so you already know, if I compound this once for 1 year, at the end of the year I got $2,400, right? Okay, let's stick to 1 year. What if I get interest twice in that year? All right, that's what we're going to do. All right, so here we go. So B1, the first new balance, okay, is still going to be 40,000 times 1 plus the APR, but you're only getting half as much. So instead of 6%, did you say it? Instead of 6%, I'm really getting 3%. Okay. So 0.03 to the, now what's t? I'm doing this for 6 months, right? 1/2. Well, now hang on. Yeah, let me not, the t is still years, right? Don't, again, let's focus on 1 year. Don't worry about the t. Don't worry about the t. That's going to get you confused. Don't worry about the t. You don't have to worry about that. Now, you know how much this is, don't you? Can you tell me in your head what this is? 40,000 times 1 is 40,000. And 40,000 times 3%? You told me a minute ago. 1,200. So this becomes how much altogether? 41,200. Okay, all right, so we know this is. Where's my eraser's on? So this is going to be 41,200 bucks. Now what's B2, the balance after the second 6 months? Well, you're starting with 41.2. But you're still multiplying by this. You're still adding 3% to that. Now, can you do that in your head? What's 3% of 41,200? But remember, percent means over 100, right? So if I take that thing times 3 over 100, the 100 cancels the 41,200 how? Get rid of 2 zeros. So you got 412 bucks, right? Now times the 3. It was 3. It times 3 divided by 100. I divided by 100. I got 41. I got 412. Now multiply that by 3. Is that terrible? It's be 1,200. Multiply that by 3. 1,236. So you see already you got more money. Before we had 2,400. Now we're getting 1,200 and 1,236. So we ended up with $36 more, didn't we? Okay. So let's write that down. So that's going to be 41.2 plus 1236 is going to be 2436. 42. 42. No, 40. Wait. 42. Wait, there's something screwy going on here. Oh yeah, I'm thinking in 1 year we had 2,400 on top of the 40,000 is 42,400. Now I'm getting 42,436, right? Yeah, that's right. I thought I was getting too much. Whoa, come back. 42,436. There you go. Right, because I'm adding 1,236 to 1,200. There it is. Perfect. Okay, good. All right, let's make this more interesting. What if I did it 4 times a year, every 3 months? Would I get more than 42,436 when I'm done? I should. That's the idea. The more compoundings you have in 1 year, the more interest you're going to get. But my question is, how much more? What's the most I can get? What's the limit of this process? So that word limit, that's important. That's coming up. If you do this infinitely many times during the year, every moment, every instant, of every second, of every minute, of every hour, of every day, of every week of the year, how much money are you going to get? All right, let's do this again. We did it for 2 compoundings in 1 year. Let's do it for 4. Okay, so B1 is going to be the original deposit times 1 plus, now, before 1 year was 6%, so in 6 months it was 3%. In 3 months, 6 divided by 2, 6 divided by 4 is 1.5, right? So instead of 0.06, it's right? 0.06 became 0.03, now it's becoming 0.015. Okay. 0.010. Hello. Excuse me. My team viewers crashed. Why did I do that? It thought I logged out for some reason. Sorry. Hang on. I must have hit the logout key by accident. You know, that's what's the problem with multi-touch. I touched two things. All right, what is it? Okay. Come on. Oh, this again? Are you serious? Sorry, this technical difficulty. I really got to get this down. This problem with this. Come on. There's something there's got to be a way to set this so it doesn't keep on changing all the time. What is it? What? 1280 by 1024? It's got 1900 by 1200. Can't I do that? All right. Anyway, 1280 by 1024. I'll have to figure this out later. 1024. There it is. There it is. Okay, we're back. Come on. We should be back. Okay. What's that? Because I'm making t equal to 1. I'm fixing t to 1, just 1 year total. We'll talk about what happens if we want to do this again for 2 years, 3 years. We'll get to that. All right. So plus, what was it? 0.015, right? Yeah. Okay, so 0.0015. Okay. And so what is that? Well, that's sort of hard to do by hand. So let's ask Ziggy. All right, Ziggy, come here. So that's going to be 40,000. Times 1, well, that's basically 1.015, right? All right. Now, what are you going to do for the next 3 months? Do you start with 40,000? You start with the 40,600. Okay. Times what? The same amount, right? So times 1.015. Now, how many months have we done already? 2 compoundings, how many months? That's 6 months, right? Because it's 4 compoundings a year, each one is 3 months. I did 2 compoundings, that's 6 months. How many more compoundings do I have to do to finish the year? 2 more. All right, so do it again. What's that going to do? What does the answer represent? The last answer, right? Isn't that what you want to start with? Isn't this what you're going to multiply by? We're doing it quarterly, 4 times a year, right? Quarterly means 4 times a year, right? And then, one more time, right? All right, so after 3 months, I got 40,600 bucks. I actually get a statement in my email, right? Every 3 months, let's say. Okay? After 6 months, 3 more months, 41,209 bucks. After 9 months, $41,827. And what are they going to put in your bank statement? To the nearest cent, right? And they're actually going to round off properly, rounding up, rounding down. So what is that? How many cents? 14 cents, okay. And then finally, at the end of the year, you have $42,454.54, which is more than what we had before. We had 42,436, and this is 54. So getting more and more and more. Can we automate this process? What are we really doing? Aren't we doing this? Aren't we saying B sub n, the number of compoundings, is the initial deposit, B sub 0, 40,000, say, right? Times 1 plus the, get rid of that, that's disgusting. The rest was disgusting, but this is even worse. Okay. Plus the APR, think about it, how did we get the 0.015? How do we get that? That was the 6 divided by the 4. Isn't that R divided by N, the number of compoundings? And then what did I do? Did I just do this over and over and over N times? I multiplied this N times. Isn't that a power? Isn't that the same thing? All right, let's see. Let's see if that's the same thing on your calculator. Ready? If I do 40,000 times 1 plus, let's do it this way, 1 plus 0.06 over 4 to, oh, 6. I said 6, didn't I? To the 4. In one swell foop, we get all 4 compoundings. What'd I do?
You multiply by 4.
Oh, what? Didn't I say to the? You know, wait, hang on. All right, keep this in your head. 42, 454.54. That's what I'm trying to get, right? All right, let's do this again. 40,000 times 1 plus 0.06 over 4 compoundings to the, do it 4 times. Do the multiplying 4 times. That's what exponents mean, right? And you get the exact same amount. Isn't that interesting? I like you. What if I want to do this 12 times a year? So we're up to what? 42,454. Now we're up to 42,467. So let's answer the question. What's the most you can get? What is the most you can get? What's the limit? Let me say this is the question I want to ask. What's the limit as n goes to infinity, n the number of compoundings, 2, 4, 12, whatever, right? Of b0 times 1 plus r, the APR, over n to the n. What if I let n get humongous? 50,000 compoundings in 1 year. 500 million compoundings in 1 year. What happens? Let's find out. That's what Ziggy's good for. Let's redo this. How about we, you know what? Let me do it this way. Y equals 40,000. Whoops. I'm not going to graph it. I'm just using this to define a function. By the way, one of the most impressive, most important innovations of the graphing calculators isn't that they can graph. It's nice. It's good. It's very important. But it's that it can do function notation. When I do on the home screen y1 of 2, or y1 of 5, or y1 of 10, that's function notation. F of 10, F of 2, right? That's very advanced for calculator. Most calculators can't do that. Graphing calculators can do that. So that's what I'm going to do. I'm going to define my function here. What is it? It's 1 plus 0.06 over x, right? Because I can't do n here. Quantity to the x, right? Okay. So if I quit that and I do vars, y vars, function 1 of 1, what am I asking? Once a year, simple interest. We knew that, right? Wasn't that your first raise in that job, right? Okay, we knew that. But then what's y1 vars, y vars, function 1 of 2 mean? What does that mean? 2 compoundings a year, right? So don't get confused. Some people get confused with this notation. They think it means y1 times 2. No, it's y1 plug into the function. Wherever you see x in the function, put in a 2. That's what it means. Function notation, right? All right, so then, and we got that by hand. Didn't we do that? And then when we did second, enter the, so I don't have to retype all of this stuff. It's not a lot. 4 compoundings, we got that. What, didn't we? Okay, let's clean this up. Mode, not float. What do I want? I'm running off to how many places? 2 places, right? Cents. So let's do this again. What's vars, y vars, function 1 of once a year, of twice a year, of 4 times a year, of 12. Didn't we do 12? We skipped 6. I meant to do 6. I meant to do, yeah, whatever. So 12 times a year. And I don't know if we rounded it off that way, but isn't that what we got? I think that's what we got. All right, now let's go nuts. How about 120 times a year? Instead of once a month, that's 120 times a year. Instead of once a month, that's 10 times a month? Okay. By the way, you can leave, this is bad. This is the one thing that's bad about graphing calculators. You can leave the parentheses out, and then it figures out, it assumes where to put it, and sometimes it puts it in the wrong place if you don't type it. I usually always type it, but in this case, it won't make a difference. How about 1,200 times a year? It's getting bigger, but is it getting bigger faster or getting bigger slower? Is it increasing concave up or increasing concave down? Is it increasing concave up, going to infinity, or increasing concave down, going to a horizontal asymptote? That's what's happening, right? It's getting bigger and bigger, but still not a lot. Oh, wow, big deal, $1, thanks. Wow. Okay. Well, how about 12,000 times a year? 1,000 times a month. Oh, wow, thanks. What did I get? How much more did I get? 6 pennies. Hey, I'll take it, hey. What's the most I can get out of this freaking bank? All right. Stick it to the man. Here we go. Oh, that's it. I'm done. That's it. That's all I can do. Okay? So even if I go to infinity, even if I do more and more and more, it's not going to change. Look, what's that, 120,000 times a month? A year? How about 1,200,000 times a year? How about 12 million times a year? It's not changing now, is it? So once you get close enough to that asymptote, you're not really getting that value, but you're so close to it that when you round off, it's not going to change. Okay? So the bank is going to give you at most $42,773.46 at the end of the year, no matter how many compoundings, infinite or not, right? The most you can get is that much interest. So remember, the original problem was compounding once, getting interest just at the end of the year was $2,400. I got it up to $73.46 more. Isn't that nice? Okay. Guess what that is? That's PERT. You brought up PERT yesterday? That's PERT. The limit is a power of E. Here we go. This is what I'm going to show you now. You ready? What is E? This is what E is. Okay. Let's say, come on. All right, so if you're doing compounded interest, not infinitely many compoundings, but 4 times a year, 8 times a year, 12 times a year, right? Regular compounded interest, okay? Your bank account is going to be B0 times 1 plus R over N to the N. And that's for 1 year. But what if you did it for 2 years? Instead of doing this 12 times, say N is 12, right? Instead of multiplying 12 times, you're going to do it for 2 years, you're going to multiply 24 times, right? What if it's 3 years? 36 times. That's where the years go. Okay? Now remember the original thing with simple interest? It was the initial amount times 1 plus R to the T, that was it. Now it's over N and to the NT. That's what's different. So when N equals 1, you still got simple interest once a year, compounded T years, right? But as N goes to infinity, this becomes, ready? This is what it becomes. Let's see, the limit as N goes to infinity of that is B0 e to the RT. And that's where E comes from. That's what E is. So, can we figure out what E is? If I'm saying that those two are the same as N gets humongous, which part of this is E? This was Euler's discovery. This is what made Euler, this put Euler on the map. And then he did a lot more stuff, but this was like his first big thing. It was actually really big. How to stick it to the man, get the most interest you can from the bank, right? Nobody knew how to do that. So if you say these two are equal for huge N, what's E actually equal to? How can I calculate E? Let's see. These two statements are exactly the same for huge N, right? This is what I'm saying. Okay, let's make it clear what I'm saying. Maybe it's not clear. I'm saying the limit as N gets crazy of B0 times 1 plus R over n to the nt is, in fact, b0 e to the rt. They're equal if n is huge. So how do I calculate e? Can I calculate e?
Yeah.
What about the b0s? If they're equal, if I want to solve for e, what can I do with the b0s? Cancel out. Okay. So let's write that. The limit. Hello, give me an m. That's an m and that's an n. Okay, don't talk to me about this. 1 plus r over n to the nt is e to the rt. So which part of this is e? That's what I'm still asking. I still don't know. Can I actually get e? Well, where's my equal sign? An equal sign right there. So how do I get e out of this? This is what Euler said. He called it, he didn't call it e, but he called it this number. I want to know what it is. This is how he got it. How did he get it? What else cancels out? Does anything else cancel out? The t's don't matter, right? What if I take the t'th root of both sides of the equation? The t's cancel out. Okay. So let's write that. Let's see. Got room here? So if for n sufficiently large, if n goes to infinity, the limit as n goes to infinity of 1 plus r over n to the n is e to the r. Oops, what happened there? Wow. I don't know. This is gonna. All right. So how the heck do I get e out of that? Apparently, e to the r is the limit as 1 plus r over n to the n. How do I get e? I want e. What's r then? If I just want e, what's r? E to the r equals stuff. E to the what is just e? E to the 1, right? E to the r is stuff. But what's e? It's e to the 1. So what's r? It's 1. So I can say that e equals the limit of this mess when r is 1. All right. So let's say that. 1 plus r over n, 1 plus 1 over n to the n, right? Okay. So the limit as n gets humongous of 1 plus 1 over n to the n, in other words, r is 1, that is e. That is e. So let's calculate e. How are you going to calculate this limit? Now before, remember we did a limit? We did the balance based on how much money you had in 1 year, based on 2 compoundings, 4 compoundings, 12 compoundings, 12,000 compoundings, right? That was a limit. The limit exists if the numbers get closer, as n the number of compoundings goes to infinity, the amount of money gets closer and closer and closer to a certain amount, after which it didn't change, right? That's called a convergence table. If the limit exists, this converges. Can I do that again? Let's do that again. Let's take a look at the calculator. What I want to do is, I want to take, let's do it again like here. I'll put it over here. What should I type in y2? I want to take the limit of y2 as x goes to infinity. So what am I going to write for y2? How do I write this in y2? 1 plus 1 over x all to the x? Okay, so I'm going to do that. Quantity. 1 plus 1 over x all to the x. All right? And then mode, I don't want to round off. I'm going to put it back to float. Let it put the decimal wherever the heck it wants. Okay? Can I plug in 0? Something to the 0 is 1, but what's 1 over 0? Yeah, I can't start at 0. So let's start at 1. Okay. So now where did I put it? Vars, y vars, function 2 actually, right? Of 1. Okay. Of, what should I write? I want to make the x's get really, really big, so how about 10? How about, guess what I'm going to put in? 100. Now the values are getting bigger and bigger, but are they blowing up, going to infinity, or are they approaching a horizontal asymptote? Let's find out. Plug in 1,000. It's getting close to 2.7 something. It was 2, then 2.59, then 2.70, then 2.71. Does anyone know what E equals, by the way? 2.71 something, and we're getting there. How about 10,000? Are those two numbers exactly the same, the last two outputs? No, if the last two outputs are exactly the same, you can stop. It's not going to change anymore. That's the limit. All right, let's make it 100,000. Are they exactly the same, the last two lines? No. See, between these two, I have convergence to the 10th place. Between these two, I have convergence to the 100th place. Between these two, I have a convergence to the 1000th place. I want to get all the convergences I can get, all the places to match up. So let's do 1,000,000. How much convergence, to what place am I converging? Tenths, hundreds, thousands, 10,000s, 100,000s, millions, what? 10,000th place, right? The 10th place, the 100th place, the 1000th place, the 10,000th place match, don't they? And then the 100,000th place doesn't, so that's no good. So it's, to the 10,000th place, it looks to me like E is, in fact, 2.7182 something, right? All right, let's see. Let's make it 10 million. They're not the same. Let's make it 100 million. They're not the same. Let's make it 1 billion. They're not the same. But look, I got more convergence. 10th place match, 100th place match, 1000th place match, 10,000th place match, 100,000th place match, millionth place match, 10 millionth place match. 100 millions and billions don't. Well, let's go some more. Now, how much do I have actually? A billion? I do. Let's throw in a 10 billion. What the heck? Ziggy's doing all the work anyway. Wow, we're almost there. Do you see it? It's almost there. The last digit's off. One more. Now, it's going to be rounding off that last place. It's going to be rounding off there, so it might be round off there at the end. But let's see at least if it matches. And we got it to match. And now, after that, I don't care how big you want to make it. It's not going to change. Now, compare that to the value of E stored in your calculator. Where do you find that? Is there an E in the calculator already? Second divide. Okay, second divide is, look at that, same thing. Or, where else can you get E? Do you see another place you can get E on your calculator?
ln.
Second ln is e to the x, so I want e to the what?
First.
E to the first. Is this the same? That is. So for our purposes, we're going to say that E is about 2.71828182 something. There's round off error in the last place, I'm not going to count it. It could round up, round down, I don't know. Okay. So whatever it is. So that's E, we calculated E. So why is E important? Because E comes up a lot in problems, especially in the banking problems, as a natural base. Now, I don't know if you remember yesterday we were doing some problems where the base was like 3 halves. What was it? There was a question, I forget. Something about decaying plutonium or something. No, it was increasing. It was a population of a city or something, right? The turtle problem. We started off with 300 turtles in year 4 and 450 turtles in year 7, and we ended up with an exponential curve of the population equaled, I think it was 175 times 3 halves to the t over 3, right? The 3 halves, that was the natural base for that problem. But in a lot of problems, E is a natural base. And if it isn't a natural base, you can always convert it to a base E problem and use the E key on your calculator to make life easy. That's why it's there. You can convert all exponential functions to base E if you want. Yeah. E is related to ln. Well, that's actually the next section, so we're gonna do logs in a minute. But all right, let's do that. Let's talk. We just did sections 4.4 and 4.5 in one swell foo. Okay. Now you're bringing up logs. That's section 5.1. So let's talk. Here we go. Any questions? How we got E? Yeah.
Not the E. What is the N
N in this particular example is the number of compoundings per year. Right.
So that's like the
So two times a year, every 6 months, N would be 2. Every 3 months, N would be 4. Every 3 months, N would be 4. Every month, N would be 12. And like that, yeah. Okay. By the way, the banker's year has how many days in it? You would say 300 what? 60, right? Why do they do that? Well, no, because leap year would actually make it more than 365, wouldn't it? It's how long is the year in days? 365? Not really. And a quarter-ish. That's not even exact, but a quarter-ish, right? Because every fourth year we get an extra day, the leap day, right? But the bankers are lazy. You ever hear of bankers' hours? If you were like the olden days, okay, this is not true nowadays, but in the old days, to be a banker was a good job because you got a decent salary and raise and benefits and whatnot. But your hours were like, you walk in at 9 and you walk out at 3, 6-hour day, or you walk in at 2 and you close the bank at you open the bank at 10 a.m. and you close the bank at 2 p.m. This was not uncommon. And they didn't work, like, what is it, TD Bank is 7 days a week or something? No, lucky if you saw them 4 days a week open. That was bankers' hours. Bankers are lazy. So they don't want to deal with this 365.25 compound. When they do compounded interest, not continuously compounded, PERT, but compounding N, the most they used to do was every single day. And they made it easy. They said, okay, 365.25, that's ridiculous. Let's make it 360. Why? Because of Babylonia. You guys don't know your history. Because of the Empire of Babylon. No? No, you have no. God, what? You guys don't know nothing about history, do you? Math and music, math and art, math and history, math and literature, it's everywhere. You can't get away with it. Get away from it. No? No idea. The ancient Babylonians broke up they invented the sundial to keep track of the time. And they invented the system there would be, 60 minutes in an hour, 60 seconds in a minute, base 60. Why? The same reason they use 360 for the banker's year. Why? Because it's a nice, easy number to chop up. If you have 360 days in a year, 2 compoundings would be 180 days. 3 compoundings would be 120 days. 4 compoundings would be 90 days. Why do you think there's 360 degrees in a circle? Same thing. Because it has a lot of factors. It's easy to chop up. Why do you think there are 12 inches in a foot? Because it's easy to chop up 12 inches to 6 inches, half a foot, 3 inches, a quarter of a foot, right? It's easy to chop up. It has a lot of factors. Why do you think there's 16 ounces in a pound? Because if I'm going to sell you half a pound of sausages, that would be 8 ounces. If I want to sell you a pound of sausages, that would be 4 ounces. It's easy to calculate in your head, right? That's why. You never knew this stuff? There's a group called the Dozenal Society. You ever hear this? Dozenal. They're saying, change everything from base 10. Base 10 is a pain in the ass. 10 doesn't have a lot of factors. 2, 5, blah. Change everything to base 12, like the English system. 12 inches in a mile, 12 inches in a foot, right? Breaking up things up into 12. 12 gross in a peck. 12, how's it go? 1 dozen is 12 eggs. 12 dozens is that a peck of eggs? 12 pecks is a gross of eggs. No, never heard of this stuff? They do this in economics, in markets all the time because it's so easy to break it up, right? So that's why the banker's year is 360 days. Why did you ask that question? See what you did? Okay, anyway. All right, so how does this have to do with logs? That's your question, right? A good question, because look, take a look at this. What if I graph, this is actually 5.1 now. What if I graph e to the x? What would you expect that to look like? Describe it. Is it linear? E to the x. Is it linear? No, what is it? Is it quadratic? No, what is it? It's exponential, right? It's a base to a power. Okay. Is it exponential increasing or exponential growth or exponential decay? Growth, okay. Because the exponent has a positive coefficient. Okay, fine. So you know what it looks like. Now compare that to this, ln of x. What do they have to do with each other? Let's see. Zoom 4. There's e to the x, like you said, exponential growth. And here's ln of x. What is that relationship? You've seen that before. Huh? What about y equals x? Yes, go with that. It's a reflection, right. ln of x is a reflection of e to the x across the line y equals x. And what does that mean? When that happens, what's going on? That's a reflection line. By the way, I never opened the door here. It's getting hot. Does it feel hot to you guys? Yeah, you get air coming in. You think the air conditioner works without doing this with. So whenever you have a curve like e to the x reflected across the line y equals x, that reflection is the what of the original function? The inverse function. Where you're physically graphing all the x and y points of e to the x, you're swapping the x's and y's and regraphing. So that if you have this point, what's this point here? Right there where it hits the y-axis. What's the y-intercept? 0, comma, give me a point. 0, comma, 1. Now swap it. What is that? 1, comma, 0. Is that on this curve? It is. Okay? Any point on here, you switch the x's and the y's, it'll end up over here. They're inverse functions. Now remember what's important about inverse functions. You can use logs to cancel exponentials to solve equations. That's what it's about, right? Just like the inverse function of squaring is square rooting, they cancel each other out. The inverse function of an exponential function is its log, they cancel each other out. Like we said, this is what we said. Remember how we defined inverse functions? We said that if, let's put it this way. If f of g of x and g of f of x both cancel out to x, then g is the inverse of f. Remember that definition, right? So if the composition cancels out. So what I'm saying is that the ln of e to the x is in fact, you tell me, it's just what? Not 1. X. And e to the ln of x is just x. Right? So this is what we're saying. We're saying that if f of x is e to the x, then the inverse function is ln. Okay? That's what we're saying. That's section 5.1, logs. Okay? Let's see. How are we doing on time? Okay. Now, is that true for any base? Let's see. Would it be true? All right, would this be a true statement? Let's see. What if I said if f of x, go away, if f of x is 2 to the x, say, not e to the x, but something else to the x. That's exponential growth, right? Okay. What's the inverse function, do you suppose? Now, what does ln mean? ln means log base e. So what would be the inverse function of 2 to the x? Log base 2. Okay. Okay? Those are inverse functions. So no matter what base you've got, there is an inverse for it, right? Okay. All right, let's do this. Let's see if you remember your log rules. Okay. What was I going to say? What is the log of 100? Now notice I didn't specify a base. I didn't write log base 2 or something, right? If I don't specify the base, I mean the common log. Now on your calculator, there's 2 log keys. What does that mean? There's 2 log keys. You really only need 1 log table, but there's the ln key, log base e, and there's a log key. Guess what? Log base 10. Okay? So, what's the log of 100? Log base 10 of 100. You tell me. Huh? I'm not hearing it. I'm not hearing the right answer. What? 2. Why? That's my question. Why? Because the log is the exponent. That means that the base of the log, 10, 2 and a power of 2 is 100. These two statements are the same exact statement. If you agree, do you agree that 10 to the 2 is 100? Then you must also agree that log base 10 of 100 is 2. Because the logarithmic statement is the inverse of the original statement. So, in other words, if I plug in 2 here for x, and I get 100 here for y, I'm plugging in 100 here for x and getting 2 here for y. I'm swapping the x's and the y's in the graph. That's all that means. So what does log of 100 mean? It means 10 to the what is 100. That's what it means. This is what it means. Ready? This is what it really means. If I start over again, if I just make this a question. If I make this a question, this is really what you're asking. 10 to the what is 100. That's what you're asking. Okay? All right. So what if I asked you this? Log, what's the log base 2 of 8? What would that be? Not, I heard 4, but you're saying 3, right? Because I'm saying, what am I asking really? 2 to the, if this is the question, right? The equivalent to, dang it. That's not a question mark. What is that? Right. 2 to the what is 8, exactly. So there's your question mark, right? Okay, so 2 to the what is 8, and of course you know it's 3, right? 2 cubed, 2 times 2 times 2, right? Okay. How about this one? Log base 3 of 1/9. This is not cooperating. Go away. Okay. 1/9. Okay. What am I really asking? 3 to the what is 1/9. Now, if I said 9, it would be easy. What would you say? 2. But I'm saying 1/9, so it's not 2, it's -2. Perfect. You got it? Right? Because 3 to the -2 means reciprocal of 3 is 1/3, then squared 1/9. 1/3 times 1/3, right? So, are you okay with logs? And realize that logs are inverses of exponentials, right? So if I plug in 2 into the exponential, well, I should say, let me fix this. If I plug in, this isn't really a 9. What is that? All right. Of exponentials, exactly. So if I plug in -2 here, and I get 1/9, what I'm doing is I'm plugging in 1/9 here and getting -2. I'm swapping the domain and the range. In one function, I'm plugging in -2. In the other function, I'm plugging in the 1/9. It's backwards. I'm swapping the x's and y's. That's all that logs do. They swap the x's and y's of an exponential function, right? All right. Let's see what else is there here. So is this a silly question? What's the log? Let's see. Or you tell me. What's the log of 10 to the 8.5? What does that have to be? This is a silly question. It's 8.5, right? Because if I don't tell you what base the log is, you assume it's base 10. So I'm asking 10 to the what is 10 to the 8.5? 10 to the what is 10 to the 8.5. The what has to be 8.5. Right? That's a silly question, right? Okay, just making sure. Because people get stuck here, but you shouldn't. Right? Log base 10 means 10 to the what is the argument, 10 to the 8.5. So it's got the what is the 8.5. How about this one? Log of 0.01. Can you do that in your head? Do you get a calculator for this? Log of 0.01 is 1? No, it can't be 1. What am I asking? 10 to the what is 0.01? This is log base 10, right? So 10 to the... See, the base of the log is the base of the exponential, right? So if it's log base 10 of 0.01, I'm asking 10 to the what is 0.01, and you say negative 2. Negative 1 isn't 0.01. Negative 1 is 0.1. Okay, so it's negative 2. By the way, if you don't agree, you can always ask Ziggy. What is the log of 10 to the 8.5? We said 8.5. What is the log of 0.01? We said negative 2, right? Because 10 to the negative 2 is 0.01, right? That's what. Okay, just making sure you know a little bit about logs. There's not a lot about logs in this chapter, just a little bit. Okay, why is it called ln? This said log, when I hit the log key, I'm assuming base 10, right? When I hit the ln key, I'm assuming base e. Okay, that's great. But ln is shorthand for something. Why don't they just say log base e? Why don't they just write log e on the calculator? So, you know, you said it was what? Natural log. So you're talking backwards, right? The n goes after the l. It's in French, actually. Logarithme naturel. Yeah, they talk backwards. They put the adjective the other way. You're saying natural log. The French guys, they say logarithme naturel, right? You're both wrong. The guy who invented the natural log, the guy who inverted Euler, his name was Napier. A French guy, you're close. So he named the thing after himself. ln doesn't mean natural log. They call it natural log because it's based on the natural base. E comes up all over the place in nature. That's why it's called E is called the natural base. So they think of this as natural log. No. Logarithme de Napier. That's what ln means. Logarithme de Napier. Logarithm of Napier. He owns it, I guess. He's getting royalties in the grave. He's dead 300 years now. So yeah, that's what ln stands for. But it's shorthand for log base e, right? So if I say log base e, hang on to your hats, it's a tough one, of e to the 5, what should it say? Damn you, what'd I do? What'd I do? I did something weird. Oh, I did sorry, that's not what I meant. ln of e to the 5. I did too many carats. What do you think that is? Gotta be 5. Right? That's the same question, same kind of question as log base 10 of 10 to the 8.5 has got to be 8.5, right? It's the same base. All right, how about, okay, so what is this good for? This is good for solving equations. Let's solve some equations. Oh, by the way, do you know some log properties? Do you know this? You probably know this. Now, who here took Math 109? The course before this. Who here took Algebra 2 and trig regions? Okay, you should all know this. Who took something else? High school math. Okay. All right, you must have seen this somewhere in high school math. What if I said, what is the log, let's say ln, I don't care what log, but let's say ln. It doesn't matter what the base is, okay? Of a times b. Do you know that rule? Right, the log of a product is the sum of the logs. Perfect. It's ln of a plus ln of b. And it doesn't matter what the base is. It could be base 10, it could be base 2. It doesn't matter as long as they're all the same base. Everything's the same base, right? So that's the summation rule. Okay, so the log of a product is the sum of the logs. Okay, do you know this rule? The ln of a over b is what? ln of a minus ln of b. And the order matters, right? So, whoops. What happened to my a? That is a weird looking a. Okay. So that's going to be the ln of the numerator minus the ln of the denominator. All right, so the log of a quotient is the difference of the logs. Do you know this rule? ln, ln of a power, a to the b, is, this is actually a simplification rule. Is there another way to write that? Do you know it?
B times ln.
The exponent times the log of the base, right? So b is ln, oh no, it's b times ln a. All right, that's going to come up. You'll see. We're going to use that, so don't worry if you don't remember it. I'm going to practice it up. Okay, good. All right, so let's solve some equations. Let's see if this is useful for solving some equations. Let's say, all right, 5, 6. Okay. What if, I don't know, I gave this, we had this solve for t, all right? What if 100 times 2 to the t is 337,000? Say this is an exponential growth problem, right? So 100 is your initial population, 2 is your growth rate, right? Exponential growth. A, b to the n, right? P0, r, 1 plus r to the t, that stuff, right? What if I want to know the number of years t before I get 337,000 crickets? Right, so say that this is a population of crickets and t is in days. So how many days does it take to get 337,000 crickets if they double every day? That's what, isn't that what it's saying? If t is in days, plug in 1, you get 200. You plug in 2, you get 400. You plug in 3, isn't that the doubling time? The doubling time is 1 day. They double every day. So how many days does it take for a population of 100 crickets, if they double every day, to get to 337,000? And you could do this graphically. Didn't we do this? We could say one side of the equation is y1, the other side of the equation is y2, one side's horizontal line, one side's an exponential. They meet somewhere, right? But can you do it algebraically? That's what this section's about. So how do you get t alone? First you would what? Divide by 100. Okay, let's do that. So 2 to the t is 3370, wouldn't it be if I drop 2 zeros? That's how you divide by 100? Just chop off 2 zeros, right? All right, now how do you get rid of the 2? Now the nice thing would be log base 2 would cancel the 2 and you get t right away. But I don't have a log base 2 key on my calculator, so I'm not going to do it that way. I'm going to use any old log I feel like. Pick your favorite log key on your calculator. Look at your calculator. How many log keys are there? 2. Pick one. I don't care. ln? Okay, fine. What if I take the ln of both sides? So I can plug in whatever craziness I get in the calculator, right? So I'm going to do the ln of 2 to the t equals the ln of 3370. Now the inverse of 2 to the t is log base 2, but I don't have a log base 2 key. That's okay. It's still going to work out. Because we know the log of a power. We just said the log of 2 to the t can be simplified as what times what? T times ln of 2, right? The exponent times the log of the base. So t times ln of 2 equals ln of 3370. And so what's your last step to get t alone? Divide by ln of 2. So t equals ln of 3370 over the ln of 2. All right, let's put that in the calculator and see how many days we got. T was in days, right? So calculator, on, clear, ln of 3370 divided by the ln of 2 is 11 days. 11.718 days, a little bit more than 11 days, almost 12 days. Okay? So if you start off with 100 crickets and they double every day, it takes almost 12 days to get 337,000 crickets. Holy moly, really? They grow that fast? You got a cricket problem in your house, right? But guess what you just did? You just demonstrated the conversion formula for taking log any base to log of any other base. Because look at the same question. Again, take a look at the same question. What if I did take log base 2 of both sides? All right, let's do it that way. Let's see. Whoops, I need another page. Let's start over. I'm going to start over. I'm going to say, okay, 100 times 2 to the t is 37,000, right? divide by 100, you get 3370. Oh, messy, messy. And then if I take log base 2 of 2 to the t, on both, log base 2 of both sides, I don't need the power rule. I don't need to say 2 times log base 2 of 2, because I know log base 2 and 2 to the t are, say it, inverse functions that cancels out to t. So what do you get? You get that t is the log base 2 of 3370. But how do you get that in the calculator? You don't. There's no log base 2 key. Because you don't need it. Because guess what it is? That's what it is. Log base 2 of 3770 is pick your favorite log key of 3370 over that same log of the base that you were in. That's going to convert it to an e to the base. It converts it. Okay, so the log base 2 of 3370 is the same thing as the log base e of 3370 over the log base e of 2. But I didn't have to use ln. I could have used log base 10. I could have just as easily have said the log base 2 of 3370 is log base 10 of 3370 over log base 10 of the 2. So I can convert from base 2 log to any base I want. So I can use any key I want, and the calculator doesn't matter. So how about this? What if I want to graph not e to the x and its inverse, but 2 to the x and its inverse? What do you have to write there? How do you graph the inverse of 2 to the x? How do you graph log base 2 of x since there's no log base 2 key? You know now. How do you convert log base 2 to log base whatever the hell you want? You have a log base 10 key and you have a log base e key. Pick one, I don't care. Do you see what I'm saying here? Look, this is what I'm saying. Okay, log base 2 of 3370 is log base I don't care of 3370 over the same log base I don't care of the base I was in. So can I do that for any x? Can I graph all of them? It's going to be, you wanted what, ln? ln of x divided by ln of 2. So does it look like a reflection across the line y equals x? Let's see. It does, doesn't it? So you really don't need 2 log keys. You don't need log and ln. All you need is 1 log key because you can convert everything to that base. Right? If you always wanted to do log base 10, you could. If you always wanted to do log base 8, you could. Even though the problem is really log base 2. Isn't it? It's a log base 2 problem. Okay? All right. So at this point, I'm going to say goodbye to YouTube. Bye-bye, YouTube. It was fun.